Alvaro Pelayo. I'm just going to talk about Atiyah connected to multivariate solution sets.
Okay, thank you very much. It's very nice to be able to speak here, and it also gave me a chance to review some of these things that I'm going to be discussing today. Okay, so the outline of my talk is going to be the following. First, I'm going to raise some questions. Then I'm going to give you some examples, and then I'm going to discuss answers to these questions. And this is what scalar and vector case mean, and you will see what it means once we get through sections 1 and 2. Okay, so here are some toy examples of the question I want to discuss. Suppose that you are in the plane and you have coordinates x and y in R2. You can ask the question, is the solution set of this equation on 2 variables, which is a polynomial equation, connected in R2? So you can very quickly figure out that the solution set of this equation is the vertical lines that go through 1 and -1, and the horizontal line, which is the x-axis. So the answer is yes, this is a connected set. Now, how about the solution of this polynomial equation, which is essentially the same as the first one, but I added a +1 on the second factor. Now, in this case, because I added a +1, I am eliminating the x-axis as a solution. So I get that this set is not connected. It consists of 2 vertical lines, so it's not connected. Okay. Now you can ask about more general sets. So for example, suppose that you are in R4 and you have coordinates x, y, z, t, and then I give you 3 equations, like these 3 equations, and I can ask you the question, is this set connected in R4? And the answer is no longer as immediate as in the previous case, right? So at least one thing I can tell you, because I wrote down the system, that 0, 0, 0 is a solution. So at least I know one solution, but I don't know what the other solutions are. I think it probably would be extremely difficult to find the solutions, but maybe we can say, or we can decide if this is a connected set or not, the solution set. Okay, so these are some motivating examples. And let me put this question in a general framework. So the framework is going to be as follows. Consider n functions defined on a manifold M, which you can think of as a subset of Rm. So we can assume that the manifold is inside of Rm. And fixed constants λ1 up to λn. Now you can ask the question, is the solution set to this system of n equations connected? So this is exactly the framework in which the previous questions I asked fit. Is this a connected subset of M? Now you can ask the question in an equivalent way, which I prefer because in this equivalent way, we will see that some tools become more evident, that you can use some tools. So you can ask the equivalent question. Are the fibers of the map capital F, which you obtain by putting together the maps F1, F2, Fn, connected? If the fibers of this map are connected, then the solutions to this set are connected. Okay, so the question is equivalent, and this is the question that I want to discuss, which is equivalent to the previous one. Okay, so there are two cases. That you can consider. One of them is when n is equal to 1, and the other one is when n is greater than 1. Okay, so I'm going to discuss first the case where n is equal to 1. So let's look at 2 examples, which I drew in a single picture. So this function f is just assigns to a point x, y, z the third component. So if you like, this is the height function. And it is defined on 2 different spaces. The first one is the 2-sphere, and the second one is almost the 2-sphere, but you punch it on the north pole a little bit, and you create a bump. So you have that like the back of a camel here. Okay. And now you see that you can ask, are the fibers of this map connected? And you can see it depends on which space you consider it. So if you consider the fibers of this map, when the map is defined on this space here, on the 2-sphere, the fibers are all connected. Here you have the fiber is a point, and then the fibers are circles until you get to the bottom where the fibers is again a point. But now, if you look at the space on the right, already the fiber over the point 1 consists of 2 points, so it's not connected. And you keep going down, and the fibers have 2 connected components until you cross this value here, this value lambda, and then your fiber becomes connected again. So here you have 2 functions, or 1 function defined onto different spaces, and the fibers in one case are connected, and the fibers in the other case are not connected. Now, what is the essential difference between these 2 examples? And of course, it's screaming at us, the essential difference, which is one of them has a bump, right? One of them has a saddle point. So this is going to matter very much whether our function has a saddle point or not for the connectivity of the fibers. So let's explore now this question in the case that the target space is not one-dimensional. So in the case that the target space is R2. OK. I can formulate the question for this example as follows. Suppose that you have the 2-sphere cross the plane, and you have coordinates x, y, z, u, v, where x, y, z are the coordinates on the 2-sphere, where you think of the 2-sphere as a subset of R3. And u, v are the coordinates on the plane. So I can ask the question, is the solution set to this system of equations connected? Or equivalently, I can ask the question, is the fiber over the point 1, 0, where capital F is this map, connected? So the map capital F is just you put together both equations. OK? And you can actually find explicitly the fiber, and it's that pinch torus. So it's a torus, it's a 2-dimensional torus. Sorry, it's a 2-dimensional torus where when you vanish one cycle to a point. Okay. So is this fiber connected? And because I just drew it, of course, it is connected. But how do you decide that in general?
Other points, and how is it going to look?
In other points, for this particular example, it's also going to be connected.
Is it all going to look like that, more or less?
They are all going to look like actually torus, so 2-dimensional torus. Some of them are going to be circles, and some of them are going to be points. Okay. Yes. So most of them, the majority of them are going to be 2-dimensional torus. Yes. But they are all going to be connected. Yeah. So you can replace the 1 and 0 there in the system by any lambda 1, lambda 2. So of course, I know that you're thinking of using Morse theory to check that something of this nature is connected. And you're right, but Morse theory for which function? Because now my capital F takes values in R2, and we know that Morse theory is for functions that take real values, right? So Morse theory doesn't apply directly, but it seems that you should be able to recover some Morse theory for functions that take values on Rn, where n is greater than 1, to answer questions of this type. So the goal of my talk is going to be to discuss a method to answer questions of this type.
Will you use the fact that you have a rotation action? Will you use the fact that this has?
In this particular case, I will not use that in general. Okay. Yeah, I will not use that in general. In this particular case, it is true that you have a rotational action. Yeah. Exactly. I'm sure you're thinking that this is the rotation on the plane, and this is the rotation on the spin, right? Yeah. So that's true. In this particular case, we have that. But in general, I'm not going to be using that. Yeah, that's a very good question. OK. So I'm going to treat the scalar curves first. And this is done with Morse theory. And Morse was a professor here, as you know, for many years, almost 30 years. And the second person that is in the title of my talk, Atiyah, was also a professor here for 3 years. So both of them are in the title. And I realized after I already had decided on the title and on the topic. So I was very happy of that coincidence. OK, so let me introduce you or review Morse baud theory. This is slightly more general than Morse theory. And that's why it has the name baud. So a function on a manifold, which is smooth. So now I'm going to focus on smooth functions. Is Morse baud if the critical set is a disjoint union of submanifolds, and on each of these submanifolds, the Hessian is transversally non-degenerate. Okay? Now, a very important particular case of this is the case of Morse functions, which is the case in which the critical sets consist of isolated points. So you don't have submanifolds, you have points. And then you just want that the Hessian is non-degenerate at those points. So you can just, if you like, think of a Morse function as a particular case of this. Okay? Now, the index, it is defined as the number of negative eigenvalues of the Hessian, and the co-index is just the index of the negative of the function. So here are two examples. I'm revisiting this is one of my favorite examples, which is the height function on the 2-sphere on the right, and on the 2-sphere where you make a bump on the North Pole. And we saw before that in this case you have disconnected fibers, and in this case you have always connected fibers. So you can ask well, let's look at the index of the critical points here. The index of this critical point here, because this locally looks like negative x squared minus negative y squared, is 2, and the same here. And here is 0, because this locally looks like x squared plus y squared. And here you have two critical points. On one of them, the function looks like x squared plus y squared. On the other one, looks like negative x squared, minus x squared minus y squared. And on the right, you have connected fibers. On the left, you have disconnected fibers. So now you're tempted to conjecture that if you don't have points which look like this, and in this case, this is index 1, so it looks like negative x squared plus y squared, then your fibers are connected. And so that conjecture is very good because it's correct. Suppose that you have a Morse baud function, and your map is either proper or the manifold is compact. And suppose that you don't have index 1, and also you don't want co-index 1. Then your function has connected fibers. Okay? So the proof for the compact case is classical, and the proof for the case where the map is proper presumably is also classical. I couldn't find the proof anywhere, and as a matter of fact, we needed this for a paper. So we were trying to do the proof for some time, and Helmut and I discussed this in some length. So I don't know where the proof for the proper case is. Presumably it's classical. I wasn't able to find it anywhere. Okay, so now maybe let me just give you a very quick idea of how you prove this result. So what you do, the first thing that you do is because your manifold is compact, assume it is compact, you have.
What's the statement again? So
yes.
You don't have any co-index. Okay.
Yes, index and co-index not 1, and then the function has connected fibers. Yes. So let me give you an idea of how to check this in the compact case. Well, in the compact case, things are nice, so flows converge. You can talk about stable and unstable manifolds, isolated critical points. So compactness is basically just to make sure that things behave nicely. Then, using the condition on the index, you can prove that the set of critical values of index 0 is connected. And once you know that the set of critical values of index 0 is connected, that coincides precisely with the fiber over the minimum, the absolute minimum of the function. And now what you do is you go to any other fiber. Let's assume the other fiber is nearby. And then you use the gradient flow to flow down. If you're nearby, you can do this. You flow down to the set of critical points of index 0. That is connected because you just proved that. And now you connect, so you connect the 2 points on the critical manifold of index 0. And now using a transversality argument, you flow it back to the original fiber. So I think this is a beautiful idea. This is the classical argument, I believe. You have to do things a little more carefully if you want to go to fibers which are far away from the set of critical points of index 0, but similar arguments apply. Okay. So here is, so far I focus on the case where n is 1. So it's the case of Morse function. And now let me go a little bit to the last topic, to the last part of the talk, which is what happens if your function doesn't take real values, but it takes values on R2, R3, or so on. And here is a picture of Atiyah, which, as we said, was on the faculty here. So this is Atiyah's, let me state Atiyah's connectivity theorem, which was proven in the early 80s. And for this, I'm going to assume that my manifold is actually symplectic. So you have a symplectic manifold which is compact and connected and is of some dimension m. And now start with a collection of functions f1 up to fn, which are smooth. And for each of them, for each of these functions, you can use the symplectic form. You can use the symplectic form to define a unique vector field, which I call h lower fi. Okay, so this is given your symplectic form. This is your fi, which is also given. Set up this equation, and you get a vector field. Okay. And now call phi I the flow of that vector field. And now put all the vector field, all these flows together, and suppose that the map that assigns to a point the point which you obtain by flowing along all these flows is actually a torus action. So suppose that the flows are periodic, of the same period. Then the fibers of the map, f1 up to fn, are connected. Okay, so this is the Atiyah connectivity theorem.
You have to assume those f's are Poisson commute, right?
Yes, you have to assume that those Poisson commute. If you have a torus action, they are going to do that. Yes, yes, exactly. Yes, yes. So this is the Atiyah connectivity theorem, and of course you're saying, okay, this is not the same because now your f1 up to fn are very particular. It's not just any function. It's correct. It's not just any function. They have to be of a particular form, but still, it's a result which is very general and applies to a lot of maps. So it's a very impressive result, which has been very influential. It's being generalized to lots of contexts. In particular, it's been generalized to some infinite dimensional cases for loop groups and stuff. Okay. So how did Atiyah prove his theorem? And of course, because of what I said before, I'm sure you're expecting that I'm going to say Morse theory, and that's correct. He did Morse theory, and the first thing he proved, or he observed, is that, well, he did the proof by induction, and the first thing he observed is that for the case in which the torus is one-dimensional, so in the case that you have just one component, that one component is a Morse baud function, and it doesn't have index and coindex 1. So he proved, and actually this result was proven, so Atiyah didn't prove this, he used it. It was proved by T. Frankel, who I believe was a member here when he proved this. So
How do you get that? Where does that come from? What's the hypothesis you get that?
say that again?
Where does this come from?
Where does this come from? So yes, so this, you have n components, and Atiyah wanted to prove his theorem by induction. So he just assumed at first that you have one component. So in that case, you have just a T1 action, which is a circle. And the first thing he observed, he did a proof by induction. So the first thing he observed is that, so he wanted to prove this statement by induction. The first thing he observed is that if you have just one component, it is a Morse baud function with the correct indices. And this is a picture of Raoul Baud, the other person in the name. And in this, he was talking here at a conference in which he was discussing momentum maps and equivariant cohomology. And then if you use that observation of Frankel, because you are on a compact manifold, you can apply the previous connectivity theorem I told you and conclude that you have connected fibers. And then you have an induction argument which has some similarities with step 1. It's very nice proof. So this is what Atiyah did. Okay. So now let me just make some final conclusions, and I'm going to try to extend the result by Atiyah to maps that are a little more general. So instead of being maps that come from a torus action, I'm going to do it for maps that come from an integrable system, which actually contains torus actions as a very particular case of it. So in this case, what is an integrable system? So an integrable system in our context is just a map from a symplectic manifold to Rn. And I'm going to require that these vector fields are almost everywhere independent. And remember, this vector field is defined uniquely by setting up this equation. Okay? And then I'm going to assume that each function is invariant along the flow of the vector field of the other function. So that's what an integrable system is going to be for us, and I'm not going to assume periodicity or anything else. So these components need not be periodic. In the case of one of the examples I showed you before, it was periodic, as you pointed out. But for now, I'm not going to assume that it's periodic. So you can have lots of different types of fibers for these systems, and here are some examples of them. So this is the pinch torus, which already appeared. There is a point. There is a circle. Here is a two-dimensional torus. You can also have other types of fibers corresponding, for example, to hyperbolic singularities. And these are the connected components of the fibers. So your fibers could be made up of several of these components. Okay, so that's what your fibers look like. So let me tell you a recent observation, a recent result for these integrable systems. Suppose that you have a manifold which is compact and connected, and suppose that you have a two-dimensional integrable system. So a system of this type I just told you, but just with two components. And suppose that you have non-hyperbolic singularities. And just think of that you don't have things that look like the hyperboloid. Okay, let's just rule out this case. And suppose that when you look at the critical set, at the set of critical values of your system, that can be deformed into something that does not have horizontal tangencies. So look at this picture here. Okay, this picture is coming from a system of the ones that the Atiyah theorem covers. The critical set is that the set of critical values is the boundary of this polygon. Okay, and you can see that it doesn't have any horizontal tangencies. So if that happens, then the fibers are connected. Okay, so you can recover as a particular example the theorem of Atiyah. And I think the proof should be extendable to Rn. And I think we discussed this a little bit the other day in my other talk. And I believe that this should be extendable to Rn, but we haven't done it. Okay, so here is another example, which you may remember from the beginning of the talk. Is this capital F is given by these two components. And before I set the first component equal to 1 and the second component equal to 2. And I show you what the fiber look like. And here is the proof that the fiber is connected. Look at the critical set. In this case, the critical set consists of this boundary here plus a point, plus the point 1, 0. Of course, how would you know this? Yeah, I'm just telling you that's what the critical set is. And you can see it has no horizontal tangencies. Okay, so our theorem applies. Therefore, all the fibers are connected. And why should we care about fibers, right? Well, at the beginning, I told you that finding the fibers of one of these maps is the same as solving a system of equations. Okay, so that's the first motivation. Second, connectivity is probably the most elementary question you can ask about the solution set of a system of equations after you know if it has some solution, for example. Okay, so what is this set connected? That's probably the most basic question. And also, there is an interesting corollary, which is that suppose that you consider your equations independently. And suppose that for some reason you know that on each of these equations defines a connected object. Okay? Now, if you put all of them together, and you can prove that the solution set of all of them together is connected, then what you have proven is that the union is connected, right? So from your knowledge of you knew before that the dynamics was connected on each fiber, okay? Now, if you can prove using the methods I just explained that the intersection is connected, then you know that the union of everything is connected. So you can travel from level to level as you wish, just by passing through the intersection, which is the solution of all the equations simultaneously. Okay? So that's another application from the point of view of dynamics. And now, more applications. Well, these integrable systems are one of the most fundamental examples of Lagrangian fibrations. They give rise to singular Lagrangian fibrations. So the fibrations in which the fibers have singularities, like, for example, this pinch torus. that I showed you before. And Lagrangian fibrations are essentially in many contexts, for example, in mirror symmetry and symplectic topology. And most of the results, or usually it is assumed, that you start with a singular Lagrangian fibration and that the fibers are actually connected already. Okay, so if you want to apply your theorem to some singular Lagrangian fibration, you have to check the fibers are connected. That's very non-obvious to check that the fibers are connected. So we have, in what I have discussed before, I'm just trying to give an attempt to answer this question in some context. So what we have discussed gives you a method to test whether a given Lagrangian fibration, whether you can apply your theorem to a given Lagrangian fibration. That comes from an integrable system. And finally, how do you prove this theorem? Well, you don't have Morse theory, but what you try to do is you try to apply Morse theory. And in order to do that, you take your system and you cook up a new function in terms of the components of your system, and you cook it up in such a way that it's proper and Morse baud, and therefore you can conclude by the previous theorem that it has connected fibers. Okay? So the philosophy is you cannot do Morse baud theory, but maybe you can play with the components of your system and form a new component which is actually Morse baud. And then if it is Morse baud, you're going to be able to conclude that the components, the fibers, are connected, and from that you hopefully can work your way up to prove that the fibers of the whole system are connected. So you cannot do Morse theory, but you can maybe try to play with your system to do Morse theory. And of course, in order to do this construction of this proper Morse baud function, you have to use a lot of things about the singularities of the system. And that was come here into play. So thank you very much.